Hello everyone, this is Group 4 with DC-DC power regulation circuits. Before we begin, it's important to understand what a DC-DC regulator will do, or what a regulator in general will accomplish. In the definition below, we can see that a voltage regulator is designed to automatically maintain a constant voltage level, despite varying input or different loads. Additionally, designs can vary between simple feed-forward designs or include negative feedback control loops. In the pictures below, there is a closed-loop shunt voltage regulator and a DC automatic voltage regulator. The picture on the right is similar to the voltage sources that we have in our labs. They are able to output a consistent voltage despite load changes, but are limited to a relatively small maximum current. There are also three popular subsets of regulators. These include the linear series regulators, switching regulators, and SCR regulators, which are used for AC voltages. Switching regulators are what we are most familiar with as we studied the topographies of a few of them. They use a switching device, usually a MOSFET or BJT, and they regulate power output by using a duty cycle. The advantages of a switching regulator include very high efficiency at the cost of a slightly noisier output. However, with control circuits, that output noise can be controlled. Linear regulators, on the other hand, are somewhat antiquated. However, they are good in low wattage scenarios. They use variable resistive circuits such as vacuum tubes, and these produce a lot of heat, so they are terribly inefficient, but they have a very low noise output. Our project requires a DC-DC buck converter that will step down a 9-volt input to 5 volts. The converter must not exceed a plus or minus 1% output ripple voltage and have a switching frequency of 20 kilohertz. The load can vary between 0.1 watts and 1 watt, while the input can vary between 8.5 volts and 9.5 volts. With these specifications in mind, we can move on to the open loop calculations. The known variables are our ripple voltage, nominal Vout, Vin, and our assumed ripple current. Since there are two cases of loads, we need to do two separate equations for each. For a power output of 0.1 watts, the inductor current and the output current are the same. With these known variables, we can determine that the current will be 0.02 amps. Moving on from that, we calculate the resistance of the load, which comes out to 250 ohms. From these variables, the input current, the input power, and the efficiency can all be calculated. With an efficiency of 99%, it's easy to see why a switching regulator is chosen for this application. For a power output of 1 watt, the procedure is identical. And after all of this is finished, we can go on to calculate the total ripple current and ripple voltage at the output, which is seen to remain in our desired specifications listed in the slide prior. The inductance is calculated and then rounded to a value that meets the project guidelines, as well as the capacitance value using the equation listed below. For the open loop configuration at 1 watt, the voltage average output is seen at 5.015 volts with a 9-volt input. Additionally, the inductor current at 25 ohms is measured at 0.205 amps with a ripple output current of 2 milliamps. The open loop configuration is pictured below. Notice the absence of the feedback loop that will be seen in future iterations. The two images below represent a change in load. At 5 milliseconds, the configuration is changed from a 0.1 watts to 1 watt. The voltage regulator reacts to the change in load by raising the voltage output exponentially until settling at around 5 volts. On the right, to account for the load change at 5 milliseconds, the current also rises and settles at 0.2 amps. The two pictures below demonstrate our line regulation. The line on the left demonstrates our output voltage when the input voltage is modulated from 8.5 volts to 9.5 volts. There is a small source of error, however, that can be seen in the 8.5 volt line and the 9.5 volt line. Due to a constant duty cycle, the buck converter is unable to create a constant 5-foot voltage between these two settings. Our load regulation is calculated to be 0.13%, while our line regulation is calculated to be 6.5%. The ideal value for both of these, however, is 0%. The circuit diagram below demonstrates the closed-loop PI voltage controller, where the Ki is tuned to 10 and the Kp is tuned to 60. The output voltage and output current for the 1-watt configuration are significantly more accurate than the previous open-loop configuration. The voltage average for the output is measured at 4.997 volts, and the output current is 0.02 amps. The load regulation for closed loop is similar as seen in the open loop configuration. However, the curve at 5 milliseconds where the load chain occurs is much straighter than in the previous open loop configuration. The same can be said for the output current. When considering the line regulation for closed loop, the difference between the open loop configuration and this one are greatly seen. The output voltage oscillates around 5 volts between the switches at 5 milliseconds, instead of having a significant error. Lastly, the load and line regulation are significantly smaller than the open loop configuration. The load percentile is calculated at 0.05%, and the line regulation is calculated at 0.04%. For the open loop configuration, the Bode plot demonstrates an infinite gain margin and a phase margin of 82.3 degrees, which is above the recommended 60-degree phase margin listed in the textbook. The large phase margin will contribute to a sluggish system when compared to a system with a phase margin below 60 degrees. The closed-loop Bode plot, on the other hand, has a phase margin of 15 degrees, which is well below 60 degrees. This can be demonstrated in the line and load regulation, where the system was able to switch between different conditions rapidly. The last configuration our group experimented with is a closed-loop PI voltage and current controller pictured below. The difference between this and a standard closed-loop controller is that it takes the inductor current as well as the output voltage into account. With this improvement, the output voltage and output current are seen to be much more accurate. Despite demonstrating a more modulating oscillation, the average voltage is significantly more accurate, and the overall ripple is also significantly smaller.